Okay, ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. Chapter 4 is on transient heat transfer. What does transient mean? It means things changes as function of time, and sometimes we will also talk or refer to unsteady heat transfer. It's the same thing. When we consider this, how temperature changes as a function of time, there are quite a few approaches that can be followed. We start with simple, going to more complicated. The simplest case is the lump system approach, a very simple equation. However, inside the body, it cannot give us the temperature at different points. So all the temperatures in the body would have the same temperature with different time steps. When can we use this approach? When the internal resistance is negligible in comparison with the external resistance. And the resistances are the conduction and convection, and typically about 10 times. That is the ratio that is being used, and that is the Biot number. The second part, or the second approach, is to start looking at geometries that mathematically we can get a solution for, but also making the assumption of one-dimensional heat transfer only. Those bodies were plane walls, long cylinders, and spheres. The solutions can be quite complicated. It's a Fourier series, but fortunately, if tau is larger than 0.2, what is tau? The non-dimensionalized temperature, then the error would be smaller than about 2%, and for those cases we have found that the first term is acceptable. It's sufficient to only use the first term. Okay, now for that first term approach, you need roots which are eigenvalues of complicated equations. You can solve it numerically or you can get it from tables. The tables in the textbook is only for n equal 1, so it's only for the first set and not for n equal 2, 3, etc. Right. And with that, we can now solve the temperature inside plane walls, cylinders, and spheres. The third part of the work is transient heat conduction in semi-infinite solids. Now, what is a semi-infinite solid again? It is a very big body. Okay, but what is big? Big is always relative. So it depends on where we want to know the behavior as a function of the big picture. Okay. So this can be the Earth, can be a semi-infinite solid, but a very important characteristic of a semi-infinite solid is that it must have a surface. Okay. And on that surface, things will be known, or there will be certain boundary conditions. In this case, the semi-infinite solid, like the Earth, is at a constant temperature, and then suddenly this temperature here changes to maybe Ts. And then we would like to know the temperature anywhere as a function of x as we go deeper only, not in the y direction or the z direction, only as we go deeper. We would like to know how does the temperature behave. How do we do it? We've started with the energy equation. Look at our assumptions in terms of one-dimensional heat transfer. So we've thrown out the heat transfer in the y and z direction, no heat generation on the inside of the body, and that is the result. How can it be solved? Well, by defining that eta, and that eta in it has x and t. And the result of that is that that partial differential equation can now be written as an ordinary differential equation. Okay. Obviously, there are boundary conditions. And in these boundary conditions, what we need to cover is that we want that the temperature, obviously, when T equals 0 is everywhere equal to Ti, except when T is equal to 0, then that temperature would be equal to Ts. So those are the boundary conditions, and we've discussed it. Now, these boundary conditions has to be written in terms of this format before that equation can be solved, and the result of that is we get an equation like this. The error function looks very complicated, but you should consider it as a function just like cosine. Okay. Or sinus. It's the same thing. And somewhere you should be able to get a solution for it. If it's not on your small computer, on your laptop, or ease, or whatever, or doing a Google, they can be solved. And the error function can be an error function or 1 divided by the complementary error function. Okay. And if the temperature gradient at the boundary or close to the wall is known, then the heat flux can also be determined. So that is the solution, a very, very simple solution. But we have to remember that this is obviously valid for certain boundary conditions. And there are different possibilities for boundary conditions. So the first boundary condition is the following. We are going to have 4 cases. And there are cases 1, 2, 3, and 4. Okay. Now case 1, if I can show it just schematically, if that is the plane surface, and that would be in an infinite direction, and that is x. Okay. So this is for case 1, and then we would like to know what the temperature is at different depths. Okay. Now for that case, the boundary condition was that temperature of the plane surface is now a constant. It is equal to Ts. Okay. And with that, we've specifically derived that equation. So that equation is valid, obviously, for those boundary conditions. Right. Now, there are other types of boundary conditions. All the detail are not given in your textbook, but only the results. But you can go and work it out yourself. The second type of boundary condition is where, again, on the surface, we now specify a certain heat flux. Okay, so the heat flux is now given. That is the second one. That would be when we maybe have a heating pad on a surface that would give a certain number of watts per square meter. Okay. The third type of boundary condition would be a convective one. Okay. So that's boundary condition 3, and now on the outside we have something flowing at a certain temperature with a certain heat transfer coefficient. It's the third type of boundary condition. The fourth one is a laser pulse, something like a laser pulse. Okay. Just for a split second, then a certain amount of energy, E, in terms of joules per square meter, will be transferred to the surface. Okay, so the result of that, ladies and gentlemen, is that each one of these cases will have different boundary conditions and will have different equations. Okay. And the equations are given in your textbook, and they are summarized as equation 445. I think 446, 447, and 448. Something looks wrong with my numbering now, but it doesn't matter. So there are 4 equations for the 4 different cases. Okay. And let me see if I can show you those equations. Okay. They're going to take too long to write out. So it's 445. Okay, so that is the first equation, 445 for case 1. It's the one that we've derived. Okay. We can see that the temperature distribution is a function of x and alpha. Okay. Then let's look at 446. It's the next one. Okay. Now we can see the heat flux there. Do you see Q dot? Okay, the heat flux is now an input. The next one, 447, would be the one with the heat transfer coefficient. Do you see the heat transfer coefficient? Sure, there it is. Okay, there's the heat transfer coefficient everywhere in the equation. Okay, and T infinite, there it is. Okay, and then the last one is the laser, which will give us that equation. There is ES, which is the amount of joules which is being transferred to the surface. Okay, so 4 different equations for 4 different types of boundary conditions, and obviously, most probably there are many more that you can go and derive. Okay. That is the theory of transient heat conduction in semi-infinite solids. Let's do a problem so that you can get a better understanding of how to apply it, and specifically this error function, how to use it, and how to do practical problems with it. So the problem is similar to example 4.6 in your textbook, but I've changed it. Okay. And the problem is the following. In areas where the air temperature remains below 0 degrees Celsius for prolonged periods of time. Okay, that's not South Africa. Siberia or something like that. Huh? Okay. Now the freezing of water in underground pipes is a major concern. Fortunately, the soil remains relatively warm during those periods, and it takes weeks for the sub-freezing temperatures to reach the water mains in the ground. Thus, the soil effectively serves as an insulation to protect the water from sub-freezing temperature in winter. Now, the ground at a particular location is covered with snowpack at a temperature of minus 30 degrees Celsius. Okay, so it's really Siberia. For a continuous period of 3 months. 3 months. And the average soil properties is given, the K value and the alpha value. Now, assuming an initial uniform temperature of 15 degrees Celsius for the ground, determine the minimum depth of the water pipes to prevent freezing. Okay, so that is a problem. So let's show it schematically. So schematically, there's our water pipe. Okay, there is the soil. Okay. And on top of it, we have some snow. And the snow is at a temperature of minus 30 degrees Celsius. Okay, now, because we do not have other information, we are going to assume that the ground temperature is also minus 30 degrees Celsius. Okay. Okay, and for the soil, okay, this, remember, is still soil. There's the water flowing through it. Okay, so for the soil, the K value is equal to 0.4 watts per meter Kelvin or degrees Celsius, and alpha is equal to 0.15 multiplied by 10 to the minus 6 square meters per second. Okay, so all this is the soil schematically, and obviously it goes on to be very deep, and this temperature, which we call Ti, is equal to 15 degrees Celsius. So that is the soil temperature. And the snow is for 3 months. Okay. So, what is the question that we need to determine? Okay. We need to determine, before we do that, let's just put in our x-axis there. Okay. So we need to determine that distance, let's call it h. Okay, h, where that temperature there, the temperature of the wall, of the pipe, 0 degrees Celsius. Okay, so do you see what I'm trying to do? It is 3 months. Okay, the snow is there for 3 months, and then this temperature is going to decrease, okay, with time. And after 3 months, that temperature shouldn't be 0 degrees Celsius, or it should just be 0. Then we know how deep the water pipe should be. Obviously, we're going to put it a little bit deeper for a safety factor. Okay, so that's a question. You understand? Elsemarie, what did I miss?
So the TI, that's the initial soil temperature.
TI is the initial soil temperature, and it would be the soil temperature up to, well, not the middle of the earth, but yes, for a very, very long time, and that would have been the temperature just before it started snowing. It's not perfect, but in general, that is the temperature of the semi-infinite solid, and that cannot change. Always remember, the temperature of the semi-infinite solid remains a constant. It can't change. No, I changed it. It's not the same. Okay, so it's not the same as in the textbook. I've made it minus 30. I've changed it. Okay. Okay. You all understand the problem? Okay. Right. So if we now look at this problem and we look at the different possibilities which are available for us to choose from, okay, then we can see that in this case, this is one of the 4 cases that this problem represents. Okay. The surface temperature is given. Okay. So it is case 1. Okay, so it's case 1, and therefore it is equation 445. Okay. And that equation gives the temperature minus Ti divided by Ts minus Ti is equal to the complementary error function of x divided by 2 times alpha T. Right. The equation, the problem to be solved. Okay. Let's look at what do we have and what is specified. The temperature, or let's start here, the time. Okay. This should be 3 months. Okay. We want to know how long it is going to take before we get to 0 degrees Celsius. Okay, 3 months. So it can't, okay. And at 3 months, we want to know if the temperature is going to be 0 degrees Celsius. Okay. And we want to know where is X. Where will that be? So after 3 months, where in the soil would the temperature be 0 degrees Celsius? Because that is the minimum depth of our pipes. You agree? That is a problem, right. Okay, now before we actually solve this, I want to show you also a graph which is figure 428 in your textbook. Okay. So this figure is also that equation. Okay. So what it gives is the non-dimensionalized temperature, which is theta, and eta. where eta is equal to x divided by the square root of, 2 times the square root of alpha t. And the equation looks like this. That is a value of 1. If eta is 0, then that is equal to 1. And then the equation does something like that. At 2, for all practical purposes, when that value is equal to 2, then the non-dimensionalized temperature would be equal to 0. Okay. Now this theta is that non-dimensionalized temperature. So it is another graphical method that can be used to solve the problem if you've done it with calculations or to check yourself with. Okay. So it's a very, very easy check of the solution of that equation. Right, let's just go back to that non-dimensionalized temperature. Okay, so the temperature we want to know after 3 months at a depth of h. Yep, question?
That's ERF, shouldn't it be 1 minus ERFC or?
Which one now?
Right above where it says, yeah.
This one.
1 minus ERFC.
Is it correct? You've got it like that, all of you? Okay. They are, in terms of the error function, this one here, you can also write it like that. So the error function, or 1 minus the complementary error function.
You've written the complementary one.
Ah, okay. Okay. Right. Yes. Okay, thank you. Now I think it should be the complementary one. Let me just check. Okay. Now it is a complementary one. Okay. Now be careful. I want to show you something, and that's a very important thing. If you look at equation 445 and the derivation of that equation there, of which the result is equation 442. Okay. Then you will see the one is equal to the complementary function in eta, and the other one, the one is the error function. Yeah, the error function, like that. Okay. The error function. But look at T minus Ts, Ti minus Ts. In the other one, it is written differently. T minus the temperature minus Ti divided by Ts minus Ti is then equal to the complementary one. So with a little bit of manipulation, you can write it in different formats. So just be careful for that. Okay. You can use any one of the two, it will still work. Okay. So coming back to the non-dimensionalized temperature, the temperature there is 0 minus 30 divided by the surface temperature, which is minus 30, minus the initial temperature, which is 15. Okay? And that is equal to the complementary error function of eta, where eta is equal to x divided by 2 times the square root of alpha t. Yep.
So your equation says Ti at the top, T minus Ti, and then Ts.
Okay. Let me just show you here. I want you to take a look at equation 442. Okay. Equation 442 is T minus Ts divided by Ti minus Ts is equal to the error function in eta, and that is equal to 1 minus the complementary function in eta. That is equation 442. Okay. Then it's the same equation, just written differently. 445 is T minus Ti divided by Ts minus Ti. You see the difference? I'm going to get to that just now. Sorry, ladies and gentlemen, there are so many people talking now, I can't hear.
So your equation is correct. It's just the top value of minus 30 must be minus 15 because we use the TI value. Top one? Top. Yeah. It must be minus 15.
Sorry. Okay. Minus 15. Is that right now? The what?
Just 0 minus 15.
Yeah. Okay. Sorry. All right. Okay. I misunderstood you. But while we are there, let me just show very carefully the difference between the two equations. I thought that was a problem. Okay. So if you look at this, then it is the complementary error function in eta, and that is equation 445. Okay. So you will see the two equations. In this case, you use the complementary one directly, but with a little bit of manipulation, you can get to the same thing. Okay. So, even with all my errors there, okay. So, with all my errors even there, so that is also equal to the non-dimensionalized temperature. Okay. So this non-dimensionalized temperature is equal to the complementary error function in eta. Okay. So that is what this equation means, the non-dimensionalized temperature. And if we calculate that, then it is equal to 0.333. Now, what would that be equal to? Okay, so take a look at table 4.4. So in table 4.4, in table 4.4, we need to know where will the error function be equal to 0.33? And that would be approximately there. Do you see? That is where eta would be between 0.68 and 0.7. Is it too small for you to see? Let me see if I can make it a little bit larger. Okay. So 0.333, it would be in between there. Okay. So from table 4.4, it follows that eta must then be equal to 0.6841. Okay. What we can also do is we can check it with that graph, figure 428. So figure 428, if we look at eta equal to 0.333, then we get also theta 0.333, then we will get eta as 0.6841, and obviously if you can read it that accurately, then you're really a liar. Okay. But you can check the order of magnitude very, very closely of your calcs. Question there at the back?
So I think if you look at the table 4.4 again, the values that you chose are not the same as the values.
Okay. Let's just look. So we are looking at where that function would be equal to 0.333. Okay? 0.333 is already 0.3362 is 0.68 already. So it's very, very close. Okay? The reason why my values are better is because I've calculated it. Okay? I didn't do interpolation because nobody likes to do interpolation. Okay. So can be calculated also with ease, and we will discuss that just now. Right. Now that we have the non-dimensionalized temperature, nobody asked you the not the non-dimensionalized temperature, sorry, eta. Nobody asked you to calculate eta. We want to know x, or the height. Okay. So eta, by definition, is equal to x divided by 2 times alpha t. Okay. Eta, we have solved as 0.6841 is equal to h, the depth that we want to solve, divided by 2 times the square root of alpha, and alpha is equal to 0.15 multiplied by 10 to the minus 6 multiplied by the time in seconds. Okay, for 3 months. Okay, so depending on how you want to do it, you can say it is equal to, okay, 3 months. There's the months. And now you have to decide how many days in a month. Okay, on average, let's say 30. So there's the days, multiplied by the hours, which is 24, multiplied by the minutes, which is 60, multiplied by 60. So the time, if you calculate it, is 7.776 multiplied by 10 to the 6 seconds. Okay, so 7.77 multiplied by 10 to the 6. And from this, we can calculate the height as 1.478 meters, or about 1.5 meters. Okay. So, 1.5 meters, even snow, the temperature of minus 30 degrees Celsius, it would take 3 months before freezing conditions would start occurring at the pipe wall. Any questions? You understand the principle? Okay. Right, what I'm going to do with you now is I am going to show you how to use ease. Okay. Okay. So if you can just give me a moment to, okay, before I do that, I'm going to do it like this. In terms of this problem, let's go and write this problem down in terms of what is given and what we need to calculate. And I will show you then how to do it in ease. Okay. So let's decide the surface temperature is equal to minus 30. Okay, it's given. And the K value is equal to 0.4, the thermal conductivity. And alpha, I can't put in an alpha symbol on my laptop, so I'm going to write it like that. Alpha is equal to 0.15 e to the minus 6. So that is how I'm going to type it in on my laptop and in ease. Okay. And Ti is the initial temperature is 15. Okay. Then, depending now how you want to calculate the months, the time, directly with this calculation, or if you want to be a little bit fancy, let's do it like this. Say the months is 3 months. The days in a month is 30. The hours is 24. The minutes is 60. Okay. So the time would then be equal to the months. Okay. Multiplied by the days, multiplied by the hours, multiplied by the minutes, multiplied by the seconds. I forgot about the seconds. Let me put in seconds here. It's equal to 60. Okay. And the temperature of the tube is 0. the temperature xt. That is what I've decided to use, temperature xt. And then I want to calculate eta. Okay, so I'm going to write eta is equal to x divided by, I don't have a square root sign really on my laptop, so I'm going to write it as 2 times, the square root of alpha multiplied by time. Okay, that is eta. And theta is this non-dimensionalized temperature. Okay, theta is the non-dimensionalized temperature. And then I'm going to write it as txt minus ti divided by ts minus ti. Okay. And then the equation to be solved. The equation to be solved is theta. Okay, and that would mean theta is equal to the error function complementary of eta. Okay, do you agree? Those would be typically the type of things we would like to put into a computer program so that we can solve it. I hope I didn't use it. Oh, there it is. Okay. For a moment I thought I've lost it. Okay. The writing is very small, but in general you will see I've done exactly that. And let me see if I can make the font a little bit larger. I specifically did try to do that. I'm going to make it 18. Okay, there it is. Okay. So the surface temperature minus 30, the K value 0.4, the alpha 0.15, e to the minus 6, the initial temperature 15, and the months, 3 months, 30 days, the time calculated like that. Okay, the temperature of the tube, so that is just a comment in brackets like that. Txt is where the temperature should be 0, and then eta is equal to that, and then to be solved. Okay, so what is wrong with this program? In terms of how you normally do programming, okay, let's go through it step by step. So everything would be fine, 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 fine. Time, okay. You haven't defined time yet. Okay, look where it is. Okay. Okay. With ease, it doesn't matter. You can put it wherever you want. Okay. Txt, okay, then that, and the calculation of that, and the theta, and then what you then should do is F2. No. Okay, if I stand here, I can't do the F2, so let me just press the F2. Okay, so if you press F2, then everything is calculated. Okay. So there is, and even look at theta. It makes the theta and the eta as it should look like. Okay. There's the calculation of the time in seconds. There's the surface temperature. There is Txt, and that is what we wanted to calculate, 1.478. Okay. Now, I want to show you that this is now the equation to be solved. Okay. If you're as confused as me, maybe you've decided that, you actually, when you started with this problem, oops, I have to, let me just, Okay, now I can do it again. Okay, so let me start with the equation. Okay, there's the equation. I actually put the equation first. Okay, and again, if I do press F2, okay, let me go to the laptop again. Everything calculated. So as long as you've got all the equations and you put in all the constants, it will automatically solve the problem for you. It's a very powerful thing to me, but it is also very dangerous. I would not recommend that you start developing a very complicated code from beginning to end. Start simple, just put in months and calculate the time and check it that it works, that it runs through. And then you start adding all the equations one by one, and at the end, it will calculate everything for you. Let's, for example, decide, well, somebody now ask us, how long will it take for the temperature to reach 5 degrees? Okay, so let's change this to 5, okay? And now the time is not given, okay? And we give x as 3 and run it, everything is solved. So you can then later on change whatever you want. You don't have to change the code at all. Okay, so that is one of the advantages for many of you that's going to do design. You're going to go through the design and then you have to start iterating again. This is very powerful in that regard. But that's not the only advantage, the fact that you can actually program in an unstructured way. The other advantage is that many of the properties are linked with the software. So if you want the thermal conductivity of water at a temperature of that, very easy. It will calculate it for you. So all the properties, thermodynamic properties, physical properties, everything is in it. And if you have tables, if you do a design and it is not a thermodynamic related type of thing, and somewhere you've got tables in which you have to do interpolation, you can put in the tables, it will do the interpolation for you automatically, it will generate graphs, stuff like that. Okay, I'm still a novice with this program, so please don't come and ask me to help you. I most probably won't be able to. I can just do a few basic things, but it is clear to me that it is actually a very, very powerful tool. The version in your textbook will not be able to do what this one does. Okay, it's not a full one. So we have the full academic version. We've sent out an email and it is available, so you can upload it on your laptop or your computer, and I think it will work for at least a year, or the term of the license agreement. Okay, any questions on the use of ease, ladies and gentlemen? Okay, later on I will also start introducing one or two more complicated cases, just so that you can see what can be done, but it will definitely not be the focus of this module. Okay, so you will have to do independently, have to master this software on your own, and I would really recommend it. Thank you very much, and then I'll see you again with the next lecture.